pleased to be here when seeing so many friends. And indeed, I've seen this place the starting time in the early 80s. And to see how it is now, it's amazing. And really, I want to congratulate all of you, John, and so many friends here. First of all, it's not exactly the title that John mentioned, because when we commented with the talk, I gave this thing, and then I forgot I was supposed to talk about that. So it's closely related, because I thought the idea was you wanted to some introduction to mean field theory. Okay? And mean field is a fantastic topic. Which was introduced by a few people, in particular the guy who introduced what is called mean field gains. I will explain what it is. In mean field theory is Pierre Lyons, son of my supervisor, Jacques Lyons, and the son is Phyllis medalist, and he had a lot of stuff, in particular in spiritual theory. But other people like Peter Gaines and his friends and collaborators. Okay, so you may be disappointed because there will be my talk will be technical by some aspects. What I want to do is my strategy is to try to show you what are the mathematical problems behind this theory. Although the most interesting things are applications, of course, I can mention a few. In my title that John mentioned, I mentioned energy, which are energy grids and energy networks. I can say a few words about that. But I'm sure here, with your creativity, your imagination, you will, I'm very interested to discuss with you, you will find very interesting application of this field. So the best I can do is to show you what are the mathematical challenges, what are the new mathematical challenges. It's really new, it's extends control theory. The good thing is that you can write the equations, we know the problem to be solved, which is of course in mathematics good, but how to solve them, we don't know. That's a challenge. That's a challenge. There are daunting problems. There has been progress, a lot of progress, but still daunting difficulties, and that's of course what is interesting. I hope my strategy is correct, but nevertheless, I will take some time to discuss the origin and the ideas, the words, mathematics, and then we will enter into the technique. How long do I have?
1 hour.
Okay. First of all, there are two theories: mean field type control and mean field gains. It has been a little bit confusing at the beginning. What's the difference between the two? First of all, in common there is mean field. What is mean field? Mean field is a concept of physics, very old concept of physics. Basically, I'm not a physicist, but what I understand is the following, and it's very easy to understand. Everybody understands that. First of all, there is a miracle in physics, which exists only in physics, not in biology, not in economics, not whatever. The miracle is the following. For 95 or 98% of physics, you need about 10 equations, and that's it. Right? You need heat equation, you need Maxwell, you need Navier-Stokes, you need things like that, and that's it. There is no analog in biology. It does not exist. The analog in biology or in economics does not exist. Why is that so? The way I understand it is because of mean field. because the difficulty is that if you take a medium, a fluid or a gas, it's of course made of an infinite number of particles. These particles move around, and if you follow, it's absolutely, if you follow, and they follow some rule of physics, of energy and whatever, and they are identical, okay? And that's it, and they interact. And that gives you a medium, a fluid or a gas. And if you try to solve the problem at microscopic level, at the level of particle, it's absolutely impossible. But because of averaging, because of the averaging phenomenon, you can average, and the problem becomes simple. At the macroscopic level, you have some kind of representative agent, we will say now in the new terminology, and you can write easy, relatively simple equations. And this is mean field. It's the averaging phenomenon, or homogenization, in some terminology that we like also. And that's it. This does not exist, does not seem to exist in biology, does not seem to exist in economics, except now, this new idea, why not in social sciences? Same thing. That's where Pierre-Louis Lyons and Jean-Michel Lasby came with this idea of games. Games, of course, particles don't play, they don't play no games, right? Games is really a different idea. It's application of its physical concept, the concept of physics, to social sciences. The idea is very simple. Individuals are like particles. You, me, we are similar. Okay? We are similar. We are like particles. We are rational people. Suppose we are rational. So we have some type of energy optimization because we have our rational objective and that's it. And we are identical, and there is some kind of, we can think of some kind of averaging effect. And instead of solving, so we play games because particles, of course, they don't decide anything. They follow a rule of physics, but we decide, and we interact, and we have our own objectives. So we have a sort of Nash games. Nash game with millions of people. Millions of people, it's impossible to solve, right? Same problem. But because we are identical, if we apply mean field ideas, we can change the problem into a representative agent, which represents the community. This agent has, of course, its own trajectory, its own objective, but because of the mean field effect, there is an impact on the behavior, the trajectory of the payoff, and this mean field effect reflects the impact of the community, of the society, the environment, and that's it. But it becomes a control problem. It's become only one decision maker with some modification of a trajectory due to the mean field effect. That's basically the idea. It's very easily to understand in traffic control. You are in a highway, you drive your car, but there are a lot of people. If you are the only one in the highway, of course you are by yourself, and that's it. You have your own, you decide what to do. But if there is a big traffic, there is a mean field effect which which prevents you to go fast and so on. Okay, that's one of the easy, immediate application of mean field theory in traffic control. Is one of them. There are more ambitious things in economics. Because you may say, after all, in economics there is equilibrium theory. Okay? In economics there is equilibrium theory. What's the difference? The difference is the following. In equilibrium theory, traditional equilibrium theory, you act, there are consumers, there are producers, and they act with respect to a price. Okay? Price of a product in the market. So a producer will produce according to his price, and the consumer will consume, will buy or sell, or buy or not buy, we're looking at the price. But the price, to some extent, is something you adapt to. And the price is fixed by equilibrium theory, of course, but supply and demand. But you look externally, it does not influence you directly. You look at it, and but it does not influence your trajectory, your decision. You are yourself. Okay. So that's the difference, because that's a limited aspect. It's an equilibrium. Like mean-field games will also be an equilibrium, but an equilibrium which does not incorporate the influence of the environment. When you think of a network, a social network, internet, or financial markets, it's different, because really there is a direct influence of the network, the environment, the community, the society on your action, your behavior, and so on. In energy, the example I was supposed to discuss, let me say a word about that. You think of a grid now, and because of the possibility of having your solar panels on your building, right? On your house, you become you are a consumer but also a producer. Okay, so you have a situation where you have a lot of producer consumers, and they provide energy to the market, and then the price of energy depends on some averaging, which will be related to all the players in this thing. So we have people in France, in Electricité de France, have taken a model from them, have designed a mean-field model for this type of action. So I'm sure that I've not been able, because I'm not very good myself in really creating new models. I'm sure that in things like consumer behavior, or maybe positioning of some kind of industries, for instance, issues like image. When you have the image of a company with respect to the image of an industry, for you, or issues like environmental issues, if you are a green energy, impact of a green energy, and your reputation, all of that can be modeled probably by models which incorporate this type of ideas. Okay, so you see mean-field games, to summarize, which is not my topic, of course. It's basically this idea of changing a crowd into a representative agent, changing the model by incorporating a mean-field term, okay? To modify the trajectory, the dynamics, and to modify the pair. Okay? It's an equilibrium because you take this impact mean-field term as given, and you act normally as an individual. And then this term is obtained by the equilibrium of all the behaviors. You can think, for instance, in control theory, a very simple thing. You know what is mean reverting, right? Mean reverting trajectory, you try to evolve according to some value. In general, in mean reverting, this value is given. But suppose the value is just the expected value of your average, your averaging value of your state, then you have a mean reverting with respect to your mean, and that becomes exactly a mean field model. Okay, mean field type control. So mean field games is an equilibrium. It's you have a standard control problem depending on parameters, and you get an equilibrium fixing the parameters by some averaging of the result of the control problem. Mean field type control is a control problem from the very origin, but non-standard. Non-standard. You know standard control theory, I guess, here. So we have a basic control problem, which is non-standard. So it's a priori completely different. But the mathematics are very similar. That's why the two theories are really, you have to see them together. I will discuss in my talk mean field type control, because it's more in the spirit of control theory. And what I want to give you is how standard control theory has to be extended to incorporate mean field type control theory. So it's an extension of stochastic control, traditional stochastic control. And what it is exactly, what is the problem, what are the mathematical problems to be solved, okay? That's the objective. So we will get the Bellman equation, we will get all of this, but as you will see, it's much more difficult, much more complex. The reason is simple, it's become infinite dimensional. Because of infinite dimensionality, of course, it's more difficult. Okay? Very good, an immediate example. The best example I can, so what's the use of mean field? You may, hopefully you have got some idea about mean field games. What about mean field type control? Give me an example of that. The basic example, the example that I like the most, is risk management. What risk management? I become involved in risk management after my experience in space, because space is a very risky business. And going to Texas, having suffered myself, not physically, but in my job, about risk in space. And decided to make a business of it, and to also start a project in risk management in Dallas. And when I teach, I used to teach stochastic control, I say to students, you know, the difference between deterministic control and stochastic control is the following. In deterministic control, you optimize what you are going to pay, because it's deterministic, so you know what you are going to pay, you optimize it. In stochastic control, you never optimize what you are going to pay, because what you are going to pay is random. And because you cannot optimize random payoff, you optimize an average. So this average will never occur. So the real cost will be different than what you optimize. This is frustrating. Of course it's frustrating, because if what is reality is very far from what you optimize, you are not happy, right? It's not very good. So that's why in finance, in many fields, people say, okay, the average is good, but we want to be sure that the variance is not too big, the spread, and so on. This is risk management. How to incorporate risk? Risk at the minimum is to incorporate variance or several moments. We know in control there is a risk-sensitive control which has been developed. It's one way you take the exponential of the integral and blah blah, and this is the exponential because it's like a characteristic function, so you incorporate all the moments of, and that's it. It's a beautiful, that's one interesting theory. Another approach is mean field type control. Why? Because suppose simply, like you may have heard of what is called the Markowitz problem. Markowitz problem in finance is a very, very famous problem. He got the Nobel Prize for that. It's a very simple problem. It's a quadratic optimization problem. Very simple. So you fix, it was static. It was static, he got the Nobel Prize. A very simple static problem.
There's still hope for us.
What's that?
I said there's still hope for the rest of us.
The economics part is not the real.
So the idea is you have a portfolio and you fix the average and you optimize the risk, which is that's it. That's Markowitz problem. Okay. If you think in terms of continuous time, if you think in terms of continuous, it becomes a little bit more challenging. And then basically you have a payoff in which you take not just the average but also the variance. And as soon as you take the variance, standard stochastic control does not work. Finished. Dead. And the only way is to go to mean field type control theory. So mean field type control is the only way to have some techniques to solve problems of control in which you want to incorporate variance, maybe other moments. Okay? And that's one of my favorite applications and justification, I think. We have been trying to apply that in some investment problems, in also taking the famous Merton's problem, Schiller investor, and incorporating risk. Okay, so that's the basic message. So what I want to do now is to enter into mathematical problems. What are the problems? What is the problem, and what are the difficulties, okay? And what exists more or less. First of all, okay, I've been playing with my friends a long time. I've also Jens Fraser from Germany, and Jan is a young mathematician from Hong Kong, with whom I work a lot. Okay, basically I will present the mean field type control theory, discuss some interesting mathematical issues, dynamic programming, and then explain what are the equations. One is Bellman equation, we will see it, but also something called master equation. Pierre-Louis Lyon says monster equation, because it's really a tough, very but that's it. It's an equation which contains everything. So, so you have to know that there exists a master equation to be solved. So there is Bellman equation, there is master equation, so the same thing, and then there is a system of Hamilton, Jacobi, Bellman, and Fokker-Planck equations. You have three types of problems to solve. Okay, they are linked. They are links. And you have to know that they exist, and of course, to solve that in full generality is impossible. But there are a lot of challenging problems, in particular numerical issues. How do you solve that numerically? And fortunately, at the end, there is a linear quadratic case, and the linear quadratic, we will solve everything, right? At least it exists in one case where we can solve everything, and it's interesting to consider this case. Okay? This is, it's a good aspect of the theory, but it's far from being the only, it's absolutely not complete. This equation will be deterministic. Although it's a stochastic control problem, as you will see, these equations are deterministic, so that will be the simple part. Yeah, if you They are already very difficult, but they are stochastic versions. Okay? more counting. Stochastic versions. And also, makes sense, games version. This is a control problem. There is a game version, stacked game version, and that makes a lot of sense if I go back to Linfield games for a minute, I say all the individuals are identical. It's maybe true for particles, but it's not true for humans, right? Between Bill Gates and me, we are not identical, right? So they are what we call big players. Okay, big players. Everybody has to follow big players. Okay. So although this is very difficult enough, but still it's just a part of much more counting problem. So there is, for mathematician, it's really good. Very interesting direction. Okay, that's basically my program. I will finish with linear quadratic, where at least in this case we can do, okay? I don't know if you have any questions, by the way, at any time on this thing. Okay, so let me first just present the problem. This is, okay. First of all, what is the measure difficulty? What is the origin of difficulties, which does not exist in standard stochastic? One of the basic difficulty, in my view, is because the argument, the space variable, will become a probability. Okay? Instead of being Rn, the space variable will become a probability. The probability on Rn. And then we have to work with probabilities, and we have to define some space in which we are going to work. There are a lot of ideas, and there are very interesting things here. I'm not totally sure that everything is completed, but there's been a lot of progress. Probably the consensus now is to use, to represent the probability measures, the functional space called the Wasserstein space of probabilities. Let's assume that this probability measure on Rn, everything is on Rn. Of course, things become simpler if you have a finite number. That's true, but we have also the scales. And there has been a lot of mathematics on this space, in particular the fact that it is a metric space, with this a lot of ways to represent the metrics, the metric, but one way which I like myself is the following. So if the distance between two probability measures is simply the if of all random variables, so it means that you have a probability space somewhere, and you take the if of this quadratic difference between all the random variables for which the probability law of x is m, the one, and the probability law of x prime is m prime, right? So that's a beautiful metric space which has been analyzed a lot, but it's only a metric space. It's not a vector space, unfortunately, and that makes a lot of trouble. Okay? So here, just to start showing the type of problem we have, in a standard control problem, we will have the drift and the volatility. So we'll have a G of x and v. We'll have a sigma, and then we incorporate an m in it, right? So there is three components, so we have functions on Rn, metric space, Wasserstein space, and the control Rd, and that's it, okay? At the level of the payoff, we have the function f, which also defines an m. That's it. So we begin like that, and then, and this this, we start to write the problem. So we change the standard diffusion, which this is the standard diffusion, except that if we did not have this n, it would become standard. We have a diffusion, gxd, sigma dw, but we have the n. What is this n? So we have a control which is can be simply adapted, and we now this n is a probability distribution of the x. Okay. So at the same time, we have a diffusion depending on the probability distribution of the x. So here it is. So this is called the McKean Vlasov equation. McKean Vlasov is an extension of diffusion. A lot of study about McKean Vlasov without controls already, because you can ask how can we solve this problem. And at the level of a payoff, we have the same thing. So we have a function. So it's an extension of the standard control problem, except that the diffusion is replaced by McKean Vlasov. And of course, the payoff, you have also this probability distribution. That's the issue. So that says, okay, it's a non-standard stochastic control problem. What can we say about it? Okay, so we just can embed. We can think of that. We do dynamic programming. We embed. In fact, the idea, basic idea, is the state. You should not consider the state as x anymore. You think in stochastic control. The state is no more x, but the probability. Okay, so it becomes infinite dimensional. And you will have an infinite dimensional control problem. Okay? Which I will discuss. But before doing that, I want to give you some ideas, mathematical ideas, which took some time to be defined properly, which I think in this context are extremely useful. So they are connected with a Strasser time space. So these are technical facts, mathematical facts, which are helpful in this general field. First of all, there is an interesting connection between probability and a random variable. It has existed all in my life. There is a weak theory, a strong theory, and a weak theory of probability. Why do we use this omega and so on? And here it comes back. So there are some interest, because what do we do with the Weissenstein? What are the techniques? So these are the very useful techniques related with Weissenstein, Weissenstein space. I try to write them here. So for instance, if you have a sequence which converges in the Weissenstein metric, you can construct a sequence of random variable in the L2 space, which is a very nice space because it's a filter space. Okay? So you have a sequence mk converted into m, then you can construct xk and x with the law of xk is mk, the law of x is n, and the Weissenstein metric is exactly different. Therefore, you have a convergence of this sequence in the inverse space. In other words, you can represent the convergence in the Weissenstein space by a convergence in the inverse space. That's extremely useful, okay? Because the inverse space is a possible inverse space. Now, the second very important thing is compactness. If you have a set of probabilities, compactness is very important because you want to get a subsequence which is converging, right? When you have, so when you have a set of probability states, when can you say it is relatively compact, which means you will extract a subsequence which is convergent in the Weissenstein space. So you have a very simple condition, which is in general easy to find. So the convergence in the Wasserstein space is very connected with the weak convergence of probabilities. But something else, you need some kind of. So these are very useful tools to handle these mathematical difficulties. A very important theorem for your cultures is Brenier's theorem, very important one. It tells you the following result. If you have a probability which is absolutely continuous with respect to the Lebesgue measure, which has a density, and if you add any probability n prime, okay, you can find a convex function which is almost everywhere m differentiable. The gradient, so it's almost everywhere differentiable, and the gradient is equal to m, such that m prime is an image of m through this gradient function, and you can express the Wasserstein metric by this thing. This is a beautiful theorem, extremely useful, and therefore it means that if you have a sequence which converges, particularly if you have a sequence which converges in this Wasserstein space, you can take a sequence of variables which converges to x, which is adapted, which is measurable with respect to the sigma 0 and sigma of x.
Phi does not depend on m?
What's this?
Phi does not depend on m prime? The function phi does not depend on m prime, or it depends on m prime? It has to depend on m prime. It has to depend, right?
This is a which is
So for each m prime, there exists a function phi, so the phi depends on m prime, right?
yes, exactly.
Okay.
Sure.
And x is, at the bottom, x is just some random variable.
Yes,
that
the
has
initial which
the
has
measure
for
in it.
m as a probability.
Yeah.
Okay, this is very. I'm just listing a few ideas which are which came in. Brenier's theorem was made in a completely different context. The Wasserstein metric space is very much studied in what is called transport theory. Transport theory, and which has nothing to do with that. But because we play with the Wasserstein metric space, tools are used. Okay, so transport theory is a lot of stuff which is totally different. How you can transport a probability with another probability, right? Okay, another idea very interesting is also due to Pierre Millions, is the idea of lifting. So to some extent, you have seen, I've already mentioned the connection between P2 and the space of probabilities and the inverse space of random variables. So you can look at the map from a random variable image to its probability. Because you have a topology involved, so it's a continuous map which is surjective. And therefore, the lifting is, if you have a function defined on P2, you can consider it as a function on H, which is very useful because it's a Hilbert space, by the simple, what is called lifting, which in X you associate U of depend on M, and instead of M you have L of X, right? This becomes map on strict H, which by abuse of notation we call it also U of X. And of course it depends only on the probability, but you can consider it as a function of H. And then that's it. So now you can, okay, the big issues are differentiation. Okay, what do we do? The interesting idea is in Hilbert space, you can write derivatives, Cato derivatives, even Frechet derivative. In these guys, it's much more complex. There is the concept of Wasserstein gradient, which is in our context not very useful. Can we use derivative in Hilbert space H when we deal with function of probabilities? That's the origin. So here the concept of derivatives which have been introduced and which play a big role in the mathematical theory of these equations which come in this business. So one thing is the idea of functional derivative. So what is a functional derivative? It's almost like Gâteau derivative. So you have a function of probability. If you take this guy, this is also a probability, right? You get another probability n prime. This is also a probability, and you can think of the derivative as 0. Then if this limit is equal to, if this limit exists and equal to a function like that, then this guy here is the functional derivative of u of n at n. The drawback with this, you have a little bit careful because if this is a it's defined at the it depends on the constant, which may depend on n, because you know n prime is a probability, so if this does not depend on x, this is 0, right? So the constant, so that's where probabilities, it will be better to change probabilities into, like in the case of nonlinear filtering, Sakai and Kushner. So you replace by unnormalized probabilities. That will be preferable. But I'm scared to do that because you have to be sure that all the mathematical results which exist can be extended for probability to finite measures, and also the contact with random variables. So, but this is in linear quadratic case, it's interesting because you can do all the calculation. This is something. Next thing is when we do the lifting, then you have a function of the Hilbert space, so you can think of this Gâteau differential. What's the relation between the Gâteau differential if u of x depends only on the law of x? What's the relation between the Gâteau differential in the Hilbert space and the functional derivative with respect to n? This is the formula. So in fact, this guy is simply a gradient of this function where you replace the argument by the random variable x. By the way, there is a big book, 2 volumes by Carmona and Delarue, big volumes where a lot of results are written. Because Pierre-Louis Lyons, you know, he used to write a lot, but now he does not write anything anymore. He just talks. He talks at the Collège de France, and they are recorded in French, and everybody has to read that. That's it. And some students write notes, and they are disseminated, and okay. So these two guys, Carmona and Delarue, Carmona is in Princeton, Delarue is in Nice. They wrote 2 big volumes where there are a lot of very useful techniques on this. Okay, so there are formulas like that. Let me just, it's a little bit, to go to a second derivative is more involved. It's more involved. So this is a formula. Okay, if you take a second derivative, you have complex formula. So but it exists. It has been done. So we can play a lot with both these formulas. It becomes very messy in the end, but there is a lot of stuff. So there has been a lot of progress. Situation is not desperate. It's complex, but not desperate. Okay, these are techniques. Let me now give you the problem. At least I can present the problem. So, Fokker-Planck equations. So, the first thing to notice is that the problem controlling the McKean Vlasov can be formulated as a deterministic problem, but infinite dimensional. So in a space of measures, that's probabilities, but it becomes deterministic. There is a stochastic analog, by the way, but let's stick to that. So these are standard notation operators. I take controls are feedbacks, as usual. Then the state is replaced by the Fokker-Planck equation. So this is a partial differential equation. This is Fokker-Planck, depending on the control. Okay, that becomes things normal. The state is infinite dimensional. You have the state equation with this guy, and you have a control which is distributed.
What is S again?
S is the time.
Ah.
S is the time. S is the time, and then we could start with T because I want Diamond. So this is a payoff. It becomes everything becomes deterministic. You see. So it's to some extent it's a control problem for PDE. Okay. Okay, then to some extent we are reassured. So we have value function, and we can write Bellman equation. That's the way it looks like. Of course, it's infinite dimensional because the value function depends on probability, and we are in the space of probability. And you recognize here the functional derivative. And this is a standard second order gradient on second order differential operator on this guy X. You average with M. Here you recognize Hamiltonian, but this guy is replaced by this gradient. And you average, and this is Bellman equation. So it is Bellman equation, but infinite dimensional. And so we have to solve it. So number one, Bellman equation. We can, so I say, as I said before, there is a correspondence between the probabilities and random variables. So we can look at the value function in the Hilbert space of the Hilbert random variable, and we can rewrite Bellman equation in this Hilbert space. So you have a Hilbert space now, which is much better. It's infinite dimensional than Hilbert space, and you have some equations to solve here. So you can work with that, really. Okay, now, because time is short, so master equation. What is the master equation? It's the equation for the derivative. So there are two of them. One is scalar, which is this guy. One is vector, which is the integral gradient. By the way, it is a general fact which I've been playing with dynamic programming for all my life, practically. I realized only recently that in dynamic programming, maybe the gradient is more important than the function. Here it's something similar because this is a gradient to some extent. It's a derivative. You see, so the master equation to some extent are the equation of a gradient. And even in traditional dynamic programming, I may discuss that if you're interested. It's probably more important to look at the gradient than the function itself. Okay, so these are a solution of equations which are very complex, but contain everything.
They are backwards or forwards?
They are backwards, yes.
Both of them?
Yes, both of them. And because they are deterministic, it's fine. When they become stochastic, you have backwards, stochastic, infinite dimensional equations, so you can play with that. It's nice, but okay, so I'm just you will we can obtain them, and of course, when you look at them, you can call them a monster equation, but at least we can write them. Okay, so this is a scalar. This is a scalar master equation. So you recognize the derivative of the Hamiltonian. So you recognize this. So at least, okay. So in full generality, it's practically. It's not out of reach, but it's not a trivial problem. But we understand what comes in. It's no big surprise. It's just we have to play with be careful because we differentiate with respect to infinite dimension. But it's okay. Let's skip that. So I skip the scalar also. Maybe time is short, so I will go to
So the vector is the one for the gradient.
The one for that. Okay. Now, okay, so Bellman equation, master equation. Next thing is a system of Hamilton-Jacobi, Bellman, Fokker-Planck. Why did I use Bellman equation and Hamilton-Jacobi? Usually you say Hamilton-Jacobi, Bellman, right? And here I use Bellman, and then I'm going to use now Hamilton-Jacobi, Bellman. It's not the same equation. It's not the same equation. So you remember the problem is a control of a PDE, right? Control of, you can say it's a control of a PDE, control of distributed parameter system. I mentioned Bellman equation, but what about contrary? So what about writing necessary conditions? Okay, optimality. Why not? You have a feedback, and you change a little bit. Try to write some Gateau differential or whatever, and try to get it 0. So we want necessary condition of optimality. All right? If the gradient of the value function, that's the derivative. Yes, yes, exactly. Yes, but it will play. It will be the of course, it's related, it will come into some contrary inversion. That's what you are saying? Yeah. Yes, sure. Absolutely. So, in other words, the message is this. The Hamilton-Jacobi-Bellman equation will be the adjoint equation when you write the necessary condition of optimality. This is true also in standard control theory. Hamilton-Jacobi, we look at it as the equation of a value function, but you could look at it also as a necessary condition of optimality, as the adjoint equation, if you write it as, in this way. And in standard control theory, there is no need to do that. Because, okay, it's true, but it's not so interesting because it gives you a value function. But here it's very important. Because so the Hamilton-Jacobi-Bellman equation which comes in is the adjoint state of when you write the necessary condition of optimality for the infinite dimensional problem. Okay, so let me give you a system immediately. Because time is short, so let me give you a system. Here is the system. So because of the coupling, now we have a system coupling two equations. One is the Hamilton-Jacobi-Bellman equation, which is this equation, in which you see it's like you recognize a Hamiltonian and so on. And here's the Fokker-Planck, so the system is coupled.
So the first one is like Lagrange multiplier, right?
Yes, exactly. The U is like a Lagrange, absolutely. Yes. Yeah. Okay, and then they are, okay, so I repeat, Bellman equation, master equation, this system. Hamilton-Jacobi-Bellman.
So one here is forward, the other is backward.
Yes, absolutely. Absolutely. It's like Pontryagin. Yeah. It's like Pontryagin, exactly the same. It's very similar.
Well,
this is the adjoint. Because this is the state equation.
Yes.
This is the state equation because M is a state.
Yes.
This is the adjoint. Okay, and this is backward. So it becomes even more interesting if there is stochastic term inside. Because stochastic. But, and now there are two ways to look at this set. One is this thing is a sort of method of characteristics to solve a master equation. Master equation is an infinite dimensional PDE.
Is it hyperbolic?
No, it's not hyperbolic, but
So why
characteristics first.
Why the name characteristic?
Well, I mean, why do I say characteristic? In a parabolic equation, characteristic can be stochastic.
Ah, okay.
It's solving an equation, a PDE, by its interpretation. So you can look at it. It's a way to if you want to solve a master equation, master equation arguments are x and m. Here arguments are only x. So it's a method of characteristic, but there is a system. The m is a function. Okay. So this one way. The other way is, if you look at the system, you want to decouple it, like in Riccati equations. Riccati, you know, in linear quadratic, decouples the system of primal and dual equations. Thanks to Riccati, you decouple it. One way of decoupling is to go back to the master equation. So all these concepts, you recover them in a more general thing. We have a few minutes?
Okay.
Okay, in a few minutes
But do you
remaining.
get anything that you can compute offline? Yeah.
What is?
Do you get anything that you can compute offline?
Okay, now computing is important. How do you compute?
I mean, can you conceptually do the same thing, like say some things can be computed offline, some things that you can...
Yeah, sure.
So which one is it?
But it remains how to solve numerically
Yes,
equations
right.
like.
Let's say Magnus in this sense to control, and we were a bit successful because we were able to say that this one can be computed offline and this one can be computed online. So we were able to say what, and then you could go and try it in numerical methods for each case.
Yeah, in general, offline you compute the
It's the
rule,
same
the
thing,
feedback. You
yeah,
compute the
right.
feedback, right? Yeah, sure, the same thing. The concepts are the same, except you are in a more fancy space. So, to some extent, we are in good grounds, but at the same time, it's much more complex. So, it's extended. Okay, I will just want to show you what we get in the linear
There's
quadratic.
something missing here. Where is the computational control?
Oh, the control is obtained from the Hamilton-Jacobi exactly like it's here, in the Hamiltonian. Control is here.
Oh, you take the minimization of Hamiltonian?
Sure, as usual.
Okay.
Absolutely, yes. It's an extension. You can look at it as an extension. It's quite complex, but an extension. And let's see what we get in the linear quadratic case, okay? Because, fortunately, in the linear quadratic case, we can solve everything. So at least one case we can do. Okay, so let's go to linear quadratic. Okay, just a comment. What happens in the standard case? In the standard case, there is no dependence on n, right?
Right.
Then the problem is decoupled. The system is completely decoupled. So you have the Hamilton-Jacobi-Bellman, as usual, and you have Fokker-Planck, depends on it, but it's decoupled. Okay? And then the value function is simply linear. So this depends. That's why we don't need to do anything. We have the standard here. Okay? One word about linear quadratic to finish. Okay, linear quadratic, I take this type of thing. Okay, where is the n here? So this is a standard. This is a standard stuff. No, I put the n instead of. So I just put the n through the mean. Okay, so the m will come in only through its mean.
No variant. No variant?
No, not here.
Ah, okay.
Not here. Of course, if you put the variance, it's different. Because it's different. No, I take only the, why not? It's a simplest case, right? Take only the mean. I represent in this field by y. Y is this guy. Okay? So if you look at that, the mean comes in y.
So here is mean is really mean.
The mean, this is
No, I mean, I'm joking, but I mean, mean is really average. Because the general mean field here is not average.
Mean expectation.
It's I mean the expectation, that's what it is. Yes, the expectation with respect to the probability. Yeah.
Right, but we have distributions, then you
No, sure. You can, that's the only one number.
Because most of the working controls is the
No, of course,
average.
no, the variance is not entering. No, I want, because if you put the variance, you can do things, but let's take the simple case, right?
No, I understand, but I'm saying because most of the controllers, when they say in theory, they do expectation. They don't study the entire influence of the distribution of the ensemble.
No, but no, but still here is a problem because it's not when you have this, it's inside the F. So it's not a standard problem. This one is not a standard. It's not a standard because
it's not the full mean field here.
Yes.
Right? Because you don't know.
This is a mean field.
It is a mean field, but I'm only playing with the mean. No?
Yes.
Right.
Yes, but it is a mean field. In other words, it's not just the expected value. It's the expected value of the cost, but inside the cost you have something. Okay.
Well, the question you're going to get later from me is why is this related? This particular case is related to risk.
No, this one is not related to risk.
Exactly,
It is related to the fact that I want to solve it.
Yes. All of a sudden you became practical.
Yeah, I want to solve it completely. I'm not saying it's related to risk. That's a basic example we can solve.
Right.
But it makes a lot of sense and it's not totally trivial.
No, I understand.
It's not totally trivial, but at least we can solve all the equations. All the equations. It may be related with mean reverting because you target your mean, target your own mean. Okay, it's a mean reverting at least. It's not risk, but it's mean reverting. Okay, and here let me just write the equation so we can write everything. The Bellman equation we can. So here that's what it looks like, and here's the solution. Here's the solution. You see how it looks like. We take the mean second order, mean here. And here we remember there was an expect, so that was the mean of the second order mean, right? So it's like a variance here, right?
It's a common one, yeah.
Yeah. And here we have the expected value, and we have some function here depends on n lambda. So that's what the solution is. And the pt will be solution of the Riccati equation. The sigma will be solution also of some Riccati equation. Let me write it here. So we have p, we recognize our friend. It does not depend on n, but the sigma is here. So we can do all calculation. I mean, it's not trivial because the sigma is not totally obvious, but we can do everything. That's a good thing. I don't have to tell you much about that, but we have we have to be careful in the fact that it's a probability and a measure. But here, because we know all the thing, we can solve it. Okay, so to summarize, we have an extension of standard control theory, okay, infinite dimensional, with a lot of possible extension, stochastic, game, and so on. Big daunting problem like how do we solve that numerically, and so on. And these are a lot of tools available, and I think we are more and more to connect that with some concrete application in which we have particular problems. I've been playing with some of them. I'm sure you may have some ideas on how to use that. So my objective again was to show you what were some of the mathematical challenges Good news is that we can write the equations. Bad news, we don't know how to solve them. But at least the problem is posed, well posed. There is a lot of progress. There's been a lot of progress in techniques, in mathematics, and so on. Still a lot to be done. Okay, I want to conclude on that.
Thank you.